Let's continue our look at chemistry. For this lecture, we'll explore why water is important for life. Remember the structure of water? What kind of bonds hold the molecule together? Yes, polar covalent bonds. Well, this gives water some really neat properties. In fact, if it wasn't for these properties, life would not exist as we know it. Remember that the electrons shared between the hydrogens and oxygens spend most of their time orbiting the highly electronegative oxygen atom? So the molecule has a slightly positive end and a slightly negative end. Well, we can represent those partial charges with a special symbol. That little squiggle is a Greek letter, the lowercase delta. In chemistry, it means partial. So when we consider a water molecule, the area around the oxygen atom has a partial negative charge, while the areas around the hydrogen atoms have slightly positive charges. Now we'll find out why this polarity is important. If we were to take a glass pipette, which contains slightly charged molecules, and place it into a beaker of water, the polar water molecules rise above the water level of the beaker. Is it magic? No, it's due to a property called adhesion. Adhesion is when one substance is attracted to another substance. In this case, the polar water molecules are attracted to the slightly charged glass and stick to the glass inside the tube. Another property helps to explain this phenomenon. Cohesion, which is the affinity of a substance for itself. The water is further attracted up the pipette because each water molecule wants to stick to other water molecules. Again, water's polar nature is responsible for this property. The attraction the slightly positive end of one molecule of water has for the slightly negative end of another water molecule forms a hydrogen bond. A water molecule can form up to 4 hydrogen bonds. And since this property is just based on polarity, hydrogen bonds can form between any polar molecules. But the cohesive property of water also helps to explain why water beads. All the water molecules are attracted to each other and want to be as close to each other as possible. So a sphere of water forms. And cohesion can also explain surface tension. The water molecules at the surface of this pond can form hydrogen bonds only with the water molecules next to them or underneath them. So the water molecules are attracted to the other water molecules around them on the surface and are also being pulled downwards by the attraction to the water molecules below them. This forms a skin of water on the surface that is hard to break through. This water strider is so light that he can rest on the surface of the water without breaking the hydrogen bonds holding the molecules together. Now, on to the next interesting property. Heat of vaporization. What does that mean? Well, think of a pot of boiling water. As the liquid water reaches its boiling point, the water molecules become so energetic that they vaporize into the air, becoming a gas. This vaporized water is what we call steam, and the heat of vaporization is the amount of heat any liquid must absorb in order to change into its gaseous state. Water has a very high heat of vaporization compared to most other liquids. Why do you think this would be the case? Yes, those hydrogen bonds between the molecules. The water molecules themselves must not only be energized, but the hydrogen bonds must also be broken in order for water to vaporize. And this is a very good thing for living organisms. So, what happens to liquid water when the temperature drops to 0 degrees Celsius? It becomes ice, the solid state of water. But something interesting is going on at the molecular level as water becomes ice. As the temperature drops from the boiling point to the freezing point of water, the molecules are doing a very strange dance. At 100 degrees Celsius, the water molecules are crazy with energy. They are so energetic they can only exist in the gaseous state, and they are bouncing around so much the water molecules are not very close to one another. As they smack into one another, they rapidly form and break hydrogen bonds. Now remember, they must be in the correct orientation, slightly positive end of one molecule to the slightly negative end of the other molecule, to form hydrogen bonds. But if the temperature drops to 50 degrees, the water molecules are not so energetic and can be much closer to one another. They like being in the liquid state, forming and breaking hydrogen bonds at a slower pace. A water molecule at this temperature might form hydrogen bonds with several of its neighbors, and slide closely past other water molecules without making any bonds. Soon it bumps into another water molecule, breaking the old bonds and reforming new ones with different water molecules. This is why water flows. But at 0 degrees, something unexpected occurs. As the temperature drops, the water molecules slow down. They form hydrogen bonds with their neighbors, but are less likely to bump into another molecule with enough force to break any of the already formed bonds. At 0 degrees, the water molecules are basically motionless. But as they slow down, each molecule formed the maximum number of hydrogen bonds with its neighbors. So each water molecule has formed 4 hydrogen bonds with other water molecules. In the liquid state, water molecules can move and get close to one another. But at freezing, they are spaced away from each other, as you can see from just a handful of water molecules at 0 degrees. The hydrogen bonds occur at a certain distance between molecules, and a structure called a crystal lattice is formed. This increased spacing results in solid water, ice, being less dense than liquid water. That is why ice floats on liquid water. This is very important. If ice was more dense than water, it would sink. This would mean that almost all the life in ponds and lakes would die every winter, at least where it gets cold enough to freeze. We have learned that water has many unique properties, mainly due to the hydrogen bonds it can form. But organisms contain more than just water. They contain solutions. A solution is a mixture of, for our biological purposes, water and something solid that dissolves in water. If we were to take water, a solvent because other substances can dissolve in it, and salt, a solute because it can dissolve in a solvent, and mix them together, we would get a solution of salt water. Now, if we look very closely at what is going on at the molecular level, we would see that the polar water molecules are attracted to the charged ions in the salt. The partially negative ends of the water molecules surround the positive sodium ions, and the partially positive ends surround the chlorine ions, breaking the ions up. This is why polar substances, those with some degree of charge, will dissolve in water, and we give substances that dissolve in water a special name: hydrophilic, which literally means water-loving. Now, on the flip side, some substances won't dissolve in water. If we put a nonpolar substance, which has no charge, such as oil, in water, it tends to clump together and repel water molecules. The special term we give to these substances is hydrophobic, water-fearing. We really can't have a solution of oil in water because oil alone does not dissolve in water. Solutions can have different concentrations based on how much solute is dissolved in the solvent. We can measure this by the solute percentage, but it is more accurate to use molarity. Yes, the moles have come back. Molarity is the number of moles of a solute per liter of solution. Say this lady is holding a 1 molar solution of potassium chloride. It is not really this color, but let's just pretend. 1 mole would be the mass number of the potassium and chlorine, which is 39 and 35.5. Add them and we find that 1 molar solution of potassium chloride is 74.5 grams per liter, as a mole of potassium chloride would weigh 74.5 grams. And on to acids and bases, which are also very important when we look at living organisms. I'm sure you know some examples of each, but what exactly determines an acid or a base? If we look at the definition, acids add hydrogen ions to a solution, while bases reduce hydrogen ions in a solution. But what does that mean? Well, let's try to figure it out by looking at an example. Let's put an acid into water. Okay, we have hydrochloric acid on the left. It is composed of hydrogen and chlorine, so it is represented by the chemical formula. And on the right, we have water. If you look closely, you'll notice that not all of the water exists as H2O. We see some water molecules that have dissociated into hydrogen ions and hydroxide ions. We can represent this dissociation of water with an equation. The double arrows show that this reaction can go forward with the molecule dissociating, or go backward, with the ions reforming into water. But keep in mind, only a very small amount of water actually dissociates. Most water molecules do not dissociate. Okay, back to the acid. So if we put hydrochloric acid into water, it will dissociate into hydrogen and chlorine ions. As you can see, this results in an increase of hydrogen ions. Now, which one increased the hydrogen ion concentration? Right, an acid. Remember, a base reduces the number of hydrogen ions in a solution, and we can determine how acidic or basic a solution is by calculating its pH. You can do this by first figuring out what the hydrogen ion concentration is of the solution. Those brackets represent concentration, and it is written in exponential form. Then, we take the negative log of that concentration. Log is short for logarithm. If the base number of the concentration is 10, then we just need to take the exponent and multiply that number by -1. Let's look at an example. If we determine that our hydrogen ion concentration is 0.001, or 10 to the -3 in exponential form, then we take the exponent and multiply it by -1. So -3 times -1 is 3. Our pH of this solution is 3. What do you think that would be? An acid or a base? An acid. If a solution has a pH below 7, it is an acid. Try this one on your own. What would the pH be? 10. And what do you think that makes it? A base. Solutions with a pH above 7 are basic. That means that 7 is neutral. Pure water has a pH of 7, as it is neither acidic nor basic. This diagram shows a pH scale with different substances, their hydrogen ion concentrations, and the corresponding pHs.